All right, rational functions. Let's have a look. So your basic rational function is this one that's sketched here. This is the graph of f of x equals 1 over x. What do we see by this function? What do we see? How could we describe the shape? What's interesting? It's reflected. It's reflected in what way? What sort of reflection? It's reflected across the x and then across the y, or across the y and across the x, or
isn't it also an asymptote?
It's got asymptotes. So what we're looking at there is if I draw this line, this is the important thing about this function. If I draw this line there, and I draw this line here, these are the asymptotes. Notice how the function doesn't touch these two lines. So all the way to, what's really important about this function is all the way to infinity in this direction. It's never going to reach and touch. Let me do that right. It's never going to touch the asymptote, which is x equals 0. And as it approaches 0 from each direction, it's never going to touch the vertical asymptote, which is y equals 0. So that's the most important part. And when it comes to sketching the function, you need to sort of show that it approaches, and this word is important. We use this word a lot for this topic. We use the word approaches. Looks like I got one extra letter in it. 1 P or 2? I think it's 1 P. Sorry, can't spell it. I'm a math teacher, not an English teacher. Approaches means it goes towards and never gets there. It's a key word for this type of topic. So we say it approaches the line x equals 0. What else do we see?
We can see that from the function given that x can't be 1.
No, if we're looking at this function here at the moment. So we're looking at this function here. This is the function 1 over x. So basically, in order to sketch this function, we have to find the asymptotes. That's the most important part, and then we sketch it approaching the asymptotes. We also need a couple of reference points, and there's a couple of really good reference points in this function. So we have a reference point here, which has the coordinate 1, 1. And we have another reference point here, which has the coordinate -1, -1. So we'll use those reference points. In the same way when we're sketching a parabola, we use the 0, 0, which is the vertex, and then the 1, 1. And then we see how that one moves around as we apply the transformations. So now we have a few transformations to apply to this and do a sketch of g of x. So what transformations do we see in this one? Let me get some vocabulary for this. What sort of transformations can you see? Explain to the person next to you. What are the transformations we see? Do we have any translations? Horizontal, vertical, stretch, compress? That's it. Do you see the transformations? Horizontal translation. So actually greater translations, stretches, compresses.
It would be equal
Functions.
Yeah, just like 0 divided by 1. That's 0. Yeah. So that still makes sense. But like, I'm saying
You can be divided by 0.
Yeah, that's it. Greater or equal.
You can divide, we didn't divide.
Okay, so then it's either or equal to 0.
Yeah.
So the absolute function, the parameter, you can't do a reflection. The y axis, you only do it with the x axis. You can with this one. All right. So first up, the order of precedence of operators usually tells you which order to apply your transformations. So with your transformations, we have horizontal stretch or compress. It's the same thing, just whether it's a fraction or not. You have horizontal translation, moving it left and right. You have vertical stretch and compress, also same thing. You have vertical translation. You can also get reflections. You can create reflections. So what have we got here? So what's the first one? We have a horizontal translation. Is it going left or right?
Left. Right. It's going left. Right.
It's going right.
No, it's going right because the H is like the negative and the negative.
Okay. So how far is it going right?
By one.
It's going right by one.
It's pretty easy to see. So here we have the vertical asymptote. Here we have the vertical asymptote. Why is this a vertical asymptote when we look at this function here?
Because it never touches that line.
How do we see it in the algebraic expression?
Because if you substitute a number into x, you're never going to get 0. Like for the y.
No. Why?
I was thinking that if you can't have the denominator as a 0, so that
You can't divide by 0. There is no division by 0. It's the most important thing in mathematics, is you can never divide by 0. I will show you this at some point why. We can never divide by 0. So what number in this expression can we not have, but of course division by 0?
1.
1. That means our vertical asymptote for that function has to be here. So this has to be our vertical asymptote. So we're going to have, wait, what have I done? I've done something horrible. How did nobody spot that? This is x equals 0. This is y equals 0. So our new asymptote is at x equals 1. So what we see here is we've got, in general form, our function g of x is of the form a bracket 1 over x minus h close bracket plus k. The h is how much it translates to the right. H is how much it translates to the right. So this has a horizontal shift right 1. So we shift horizontally right by 1. That's the first transformation. Sorry. The word shift and translation are synonyms. You can use either of these two words. I'm tending to use shift because it's got less letters in it, and I can spell it better. You guys are dull today. No laughs. Next. So what we're going to apply next is this 3. We're going to apply this 3. What does that do? Vertical stretch. So it takes every point and moves it up by 3. So if we take our reference point 1, 1, our reference point is now firstly moved over to here, so it's moved to there, and this one's moved to there. That's horizontal shift right. Next, we're going to do vertical stretch. Vertical stretch. See in there somewhere? Factor 3. So at this moment, with just a horizontal shift, if you think about the order of precedence of how you evaluate the expression. So if I put in this point here, which is now 2, 2 minus 1 gives us 1, 1 divided by 1 gives us 1, and then we'll multiply by 3, which moves it up by 3. So this point, instead of having the y value of 3, take the y value and multiply it by 3. So that would give us 1 times 3. It's going to go to here. Take minus 1 times it by 3. Where's that going to go? It's going to go there. So this is our horizontal, our vertical stretch factor 3. And if we're evaluating that expression, we're evaluating this expression here, the last thing we're going to do is we are going to add 2 to everything. And if we add 2 to everything, what's that going to do to the function? It's going to give us a vertical shift. So our last transformation is the vertical shift up and by 2. So that 2 here at the end is going to give us a vertical shift up by 2. So our point is there now, and it's going to go there. Our point is at -2, so it's going to go up by 2, and it's going to come back to there. So our final 2 reference points are there and there. So what about the horizontal asymptote? Where is that going to go? So would the horizontal asymptote, that's this one, would it get shifted right and left? That can do, but we won't notice the difference. Is it going to get stretched upwards? No, because 3 times 0 is still 0. Is it going to get shifted upwards? Yeah. So our horizontal asymptote is going to go up by 2, and it's going to be here. So there is our horizontal asymptote. This is now y equals 2. Now I've got all that writing in the way. I wish I had my iPad so I could shrink. I could do the loop like this and just shrink it. I don't know if you guys use an iPad. No. The software is appalling. Let's just move this. Nope. All right, I gotta hope for the best. So now I need to draw my function going through these points and approaching these lines. So when it comes to these lines, make sure that you show the asymptotic behavior. That means that it has to approach the line. You have to, with this function, when you sketch it, you have to really make sure you can't go like this. What is wrong with this?
It's not approaching it, it's like going back down.
Yeah, if you look in this region here, it's pulling away. So really make sure you show it going towards it. One trick I do sometimes when I'm going towards it and I can't quite keep it going towards it is I just use my rubber and make the line shorter. So if you start pulling away, normally what I would do is I would erase the curve and the whole function, the whole thing at this point, if I can't quite make it show. So let's draw it now. So we have to show the asymptotic behavior to come up, we have to go through that point and then show it there. Likewise on this one, we have to go along the edge of here, up through that point, and then heading up in that direction. And this is how the function is going to look. So always use the asymptotes of this function to help you sketch. Always use the asymptotes. So here's the function again. What are the asymptotes? This asymptote is x equals 1. This asymptote is y equals 2. Can we see these two numbers in the function?
Yeah.
This asymptote here, the vertical asymptote, this is called the vertical asymptote. This is given by the denominator. You take the denominator in its entirety, set it equal to 0 and solve. So take the denominator in its entirety, set it equal to 0, because you're trying to find what number will generate a 0 in the denominator. So set it equal to 0 and solve, and you'll find all of the asymptotes, if there's more than one. Hannah, are you seeing this? The other one, well, it's this number at the end. It's this number at the end.
Horizontal.
The horizontal asymptote is this number here at the end. So on the polynomials, that number at the end is the y-intercept constant. That number is the y-intercept constant on a polynomial, but on a rational function, it's the horizontal asymptote. So this is the horizontal asymptote. Okay, have a go at this one for yourself. Have a go at this one for yourself. Identify the transformations, sketch the function. We'll have 5 minutes for this one. I'll just pause the video for a few minutes. Let me just say, when it comes to drawing it, I know I've got a scale drawn on mine and correct grid. When you're sketching, if the key word is sketch, then don't use a scale. Draw your axes, label your key points, but draw no scale. So don't go around marking a scale when it says sketch. You only put accurately with a scale when the key word is draw. The two words mean different things. So sketch is a rough thing, no scale required. The word draw means you draw an accurate diagram and you plot the points accurately. On this one, we're just plotting the asymptotes and the 2 key points, reference points. Okay, so we wish to look at our transformations. Firstly, what is going to be our vertical asymptote? Our vertical asymptote is going to come from the denominator set equal to 0, which implies that x equals minus 3. This is our vertical asymptote. Put that in first. What is our horizontal asymptote? Our horizontal asymptote comes from this number here at the end. So we're going to have y equals minus 1 as a horizontal asymptote. Always start with these two. It will help you position your function. Next, you need to figure out your reference points. So in our reference point, it normally goes through 1, 1. So this has been shifted 3 to the right by the horizontal shift to the right by 3, goes to here. Then it's been doubled, so it goes up to there. And then we've taken 1 away, and it comes back to there. So it's going to go through this point here. Our other reference point is this one. Our other reference point is here, at minus 1, minus 1. So we've shifted to the right by 3, so we go 1, 2, 3 to the right, it's going to be there. We then have to double it, so it goes there, and then we have to bring it down by 1, so it goes there. So our function needs to go through these points when we do our sketch. Make sure you do your sketch without a scale. Just show the asymptotic behavior, go through the point, and then towards this. A little bit trickier here on this one, so I'm going to come down through there and across. So when you're drawing a function like this one, I'm really struggling to show it in this direction. What I would normally do is I would just use my ruler and make the scale a little bit shorter in this direction, because I don't need it to go in that, and it makes it easier to show the asymptotic behavior in that direction. So I'm just going to try and do that one more time. It has to be a single smooth line. When you're drawing this type of curve, always put your arm on the inside of the curve. So if you move your paper around on the page, on the table, so have your hand on the inside of the curve, because your hand in this direction produces a natural curve anyway. And then when you want to do this one, have your hand on the inside of the curve in this direction. I'll help you sketch. So it's a little harder with me on the board like this, but there we go. Miles off. I lost it. Okay, drawing upside down in this direction, not so easy. There we go. Like that. So the curve should look something like this. Let's just skip back. I want to have a little go at. Oh no. We've got X. Let's have a go at this question. We're not sketching this one. We're just finding the value.
You just put 2 equals function.
Is that this question? Some other question. Alright, not the, sorry, I don't have this one on the slide, I just added it.
Awesome.
That's great. You should not have G of 2 equals.
No, it's that's right. Oh no, I was doing to do that.
Independent success to this.
No.
No, sorry, Alright, let's have a look. So G of 2 is 3 bracket 1 over, we put the 2 in here like this. So we start by inserting the value. Next up, how do we evaluate this? Well, the first step we do is that, 2 minus 1. The next step we do is this. The next step we do is this. And then our final step is that. Why do I do this? This shows you the order of precedence of your transformations. So your first transformation is this one. This is your horizontal shift. So your horizontal shift comes first. This is your horizontal shift transformation that's happening here. Your next transformation is this one. This is your vertical stretch. And then your last transformation is this one. Vertical shift. The order of precedence of the transformations is given by the order of precedence of the mathematical operations in the evaluation of an expression. All right, next up. We want to rewrite the function f of x equals and graph it. So what have I said here? No sense. We want to rewrite the function g of x in the form f of x is given like this and then graph it. So the task here is to rewrite this function in that form. How do we do it? How do we do it? What we're going to do is we can use polynomial division for this. So we have a division that we need to do, so let's do that. We've got 3x minus 4 is being divided by x minus 1. What do we need to multiply x by to get? I am recording, so okay. What do we need to multiply x by in order to get 3x? 3? 3 seems sensible.
No, yeah.
3 seems sensible. So we multiply 3 by x and we get 3x. If we multiply 3 by minus 1, Isa, can we do this one? What do we get? 0?
Minus 3 is a.
Minus 1 times
Okay. We do the subtraction now. What will we get from the subtraction? I'm not asking you, mate. I'm not asking you. Is there anybody else I can ask?
Let's we're going to subtract first.
Minus 1. It's minus 1. It's minus 1.
Minus 1.
Minus 1.
Minus 4 minus 1.
Minus 1. It's minus 1. What does that mean? What does that mean? That means that oof.
Wait, you write it as a fraction?
That means that this function
Then you could do it plus minus 1 over x.
3 by x to get.
Oh.
Because I was looking at the 4 by x.
so when we do this division, we get 3 remainder negative 1. So that remainder would be then further divided by this expression. So we're going to get this. We're going to get this. Can we have a go at sketching that now?
It's very simple strength. The sum is first. Now we're ready. Yeah. Yeah. So the function will be so y is equal. Yeah. Y is equal to. Yep. Yeah. So it's y be equal to negative 1. Last simple. No.
Are you talking about the vertical or the horizontal? The vertical asymptote is always x, so it would be what? It would be what?
X is equal to negative. So now the denominator will be 1. Oh, because we're looking at the
What value of x makes the denominator 0? 1. So what about the horizontal asymptote?
It's equals
Y equals
0. No. 3. Negative 3. Negative 3. Oh, so it's equal to 3 and the function is reflected. Is the function reflected?
yes.
So do you draw the asymptote as a dotted line?
Yeah.
value, any value of x, it's better to be closer to asymptote. Put it into the function, you get the value of y equal to 1. Yeah, so you want, for example, you took x,
Can we just put it as one?
so 1.
Like, we always put it as one and one and
Yeah, it's impossible.
And then
So
it
what
is
it's you just don't take that. Just don't take it. It's asymptote. You don't take the asymptote. You need to take the two closer to the asymptote. Get two. So 1 divided by 2 is 1 over 1. So 2 minus 1. Yeah, so it's 3. So it's 2 3. It's 2 3. But 1 divided by 1. 3 minus 1 is 2.
You said,
I literally ate something here. Those circle remains is 2. 2 twos. Okay.
okay, one more minute for this.
Zero. Zero negative 4. 0. No, literally, it wasn't possible to be there. It should be there. If you take 0, it's going to be 4. How do you get negative 4? I'm on the zeros. It's clear. That's all. They pass like full, but
So here in the original function, you can see the vertical asymptote here, x, because take the denominator, set it equal to 0, there's the vertical
I
asymptote.
want to know why we're, because like in the project, that was in the brackets that we use for the horizontal source. Because it's also true, it's saying it like it's which is
It is used for the horizontal, because the vertical asymptote is shifted horizontally. The horizontal asymptote you don't notice any horizontal shift. You only notice the horizontal shift in the vertical asymptote. The horizontal shift, that's the part of the function. The shift is you might think I think we can multiply by 2. I'm multiplying that.
yeah,
That's what it is. Hopefully, if I do a few more examples, you get it. Sophie.
fail, you have to let the Greeks go all the way.
Just multiply the y value. So let's say there's y value by minus 1.
So it's 4. You just leave them in trees.
Exactly that question. Rewrite this function sketch. So these learning outcomes tell you what the exam questions will be. So you can identify the transformations in a rational function, and then you can sketch the rational function. So those are the two things that you could be asked. It's like, what are the transformations in this function? The function can be given in either of the two forms we've seen so far. The simpler form, where you see the transformation, or the one that needs dividing first. And that will get you. And then you can solve problems. We haven't done that yet. All right, so let's have a look at the. Let me just see, am I still recording? Yep. All right. So let's have a look at our sketch. We need to move our points around. We have this point which is 1, 1. We've got 3 transformations. So we see our first transformation, we see it here. This is transformation number 1, which is a horizontal shift to the right. So this is a horizontal shift to the right. So this is shift right by 1. So we go across by 1, we come here. Next, we have this transformation. Next, we have this transformation. This is a vertical reflection. In the x-axis. So the point gets reflected down to here as a reflection. So instead of it being 1, it becomes -1. So this is the point 2, 1, and it will come down to 2, -1. And so any number on the outside, the value of A will have your reflection, your stretch, your conquest. You simply multiply the y value, which is 1, by that number, and then plot it. So I multiply this y number here by this letter there, and then plot the new point with the new x value. So we go here. Lastly, we have this transformation, which is, let me use some space for things. We have this transformation, which is vertical shift. Up by 3. So we're at -1. We need to go 1, 2, 3. So this point here, 2, 2, is where our function will pass through. So this bit that's normally up here in the first quadrant is now going to be translated down here. Let me just clean that up. So we are going to go from here through, let me plot the point so I can see where I'm going. We're going to go through there. So we start down here, we go through there, and we go off in this direction. Our other reference point is -1, -1. -1, -1. It shifts 1 to the right, so we go here. It shifts 1 to the right. We then reflect it in the x-axis. So if we reflect it in the x-axis, it goes here. And then finally, we do a vertical shift up by 3. So 1, 2, 3, it goes here. Then we will draw our curve. Okay, one last one for you to try. Have a go with this one. I'll pause the video for 5 minutes. Okay, so first up we need to do our polynomial division. We've got 4x plus 11 divided by x minus 2. What do we need to multiply x by to get 4x? 4. So this gives us 4x minus 8. We do the subtraction and our remainder is 19. So g of x can be written as 19 bracket 1 over x minus 2 plus 4. Did we get this? Yes. So now we want to sketch it. And we do the sketch a bit easier. So first off, when we sketch, we use a ruler. Here are the axes. Next, we want to calculate the asymptotes. The asymptotes are easy. I'm going to show you how to cheat a little bit. Pay attention on this one. Okay, so we can see that the asymptotes from this one is x. Here on this one, we can, come on, give me an in red. The asymptote is x equals 2, y equals 4. We see it here. We see it here in the denominator. Whatever sets the denominator equal to 0 is our asymptote. The vertical asymptote is this quotient. So, what happens with the asymptote? That is the value that that y approaches as x approaches infinity. It's the end behavior. So if we consider the end behavior in this direction, what's happening as we approach infinity? As we approach infinity, g of x is going to basically become 4 over x as we go towards infinity. Because 4 times a really big number plus 11 is almost the same as 4 times a really big number. That plus 11 in terms of infinity is meaningless. On the denominator, infinity minus 2 is still infinity. 4 lots of infinity plus 11 is still 4 lots of infinity. So as we go, the end behavior over here, as we go towards infinity, infinity is so big that adding 11 to it or taking away 2 makes it not change in the slightest. Not in the slightest. So the function simplifies to this, which means as we go towards infinity, it's going to give us this one. If you want the notation for this correctly, we would say the limit as x approaches infinity, the limit as x approaches infinity of 4x plus 11 over x minus 2 is equal to 4. We can see that as we get bigger and bigger, it's going to approach this value. So what this tells us is here at this point, you can still see the horizontal asymptote and the vertical asymptote. So even without doing this breakdown here, you can see the horizontal and vertical asymptote. And the reason I tell you this is if you're asked to do the breakdown into that format, you can spot if you've made a mistake because you already know what the answers are going to be from over here. Okay, so that's that. Can I shrink this? No, shrink. Sorry, I'm just trying to make some space. Software doesn't let me do it very easily. Okay, what else do we want to look at? We want to look at these 2 points. So our reference points are 2 reference points for plotting are 1, 1 and -1, -1. Those are our 2 reference points. So what are they going to be when they're transformed? So the last couple of times I've shown you how to do the transformation, thinking about each particular transformation. There is a quicker effect that we can do. So the horizontal translation is easy to spot. What is the horizontal translation?
2 to the right.
So if we move this 2 to the right, we're going to go there. If we move this 2 to the right, where will we go? We'll go here. Is that right? So then all you need to do is, what is g of 3? G of 3 is 4 brackets. It doesn't matter which of the two forms I use, will give me the same answer. What's 4 times 3? Plus 11? Divided by 1? So it's going to go through 3, 23. So we'll plot that point. It's up here. This is, well, I need a bit of space, more space. So plot the point here, 3, 23. What about the other one? What is g of 1? G of 1 is going to be 4 plus 11 over 1 minus 2. 4 plus 11 is 15. 1 minus 2 is negative 1, negative 15. So our second point is going to be there. So it's going to be down here at 1, negative 15. Next, we need our asymptotes. Our asymptote, we got this one here. Well, that's a bit close. Wait, let's do it down here. There. We got one there, and the other one is here. Label the asymptotes. X equals 2, and y equals 4. And then draw your curve. Done. Last question. Have a read of this one. See if you can write out the function.
I'm wondering, will this student be on nature or will it be on the like semester exam?
What's your guess?
I'm honestly gonna just. And they'll be on the semester.
What is the range?
I don't know. And then yeah, it's not right now, you know. It's right, I think it's at the beginning of December. Have a go at writing your function. It's a little easier.
Scale after yeah.
If you go to the limit, so it would be x minus 3.
Yeah, I know. So 300 times 1 over x minus 300.
So you focusing on
I got the question, it goes to 220 divided by x divided by x. You don't multiply.
You can multiply by 300, it's gonna be like 20,000.
Yeah, I didn't say it. We'll multiply.
Yeah, he's saying multiply. So, then, you do 300 as something you add or subtract. 220.
So x minus 300.
No, right here.
Yes.
All right, let me show you how to solve the problem. Then use the calculator for this one. Okay, let's start off with x. What does x represent in our question? Number of people. What is f of x going to represent?
The cost.
Now be careful in this. The cost with respect to who?
One person.
We want the cost what one person will pay.
Yeah.
So the way that this question is worded, we don't want the total cost. The total cost will give us a polynomial function. We want the cost that one person will pay. The cost to for one person. So this is it says here, so the total cost for each person. So cost for each person, not total cost. It's not total cost, it's the cost for each person. So the cost for each person is calculated by dividing the cost for the car by the number of people. So the cost for the car is going to be 220. We have to divide that by the number of people. So that is shared amounts. But every person has to pay for their own thing at the beach resort. They all have to pay for their own accommodation. So the cost per person is going to be 300. So here is our function. We shall use our graphing calculator now. Pull out your graphing calculator. Don't have to make this too hard. Press on. Put a new document. So you note of that. Graphing calculator. We switch them on. Take out your graphing calculator at this point. You need to practice pressing the buttons. When I let you guys use a calculator for your major, it may be worse. You should practice using it. Learn how to use it. Okay, so the first thing we want to do is press Control, add a page. So we can add a graph. Here on the graph, we can add in this function. We press Control and use the division symbol to get the quotient up. We want 220 divided by x plus 300. Why don't we see the function? The scale is all over the place. So let's just do some quick calculations. How much is it going to cost for one person? 520.
Yeah.
Is it going to cost less for more people?
Yeah.
So the maximum value we need is about 520. Can we have 0 people?
No.
You can't share the cost of a car between no people. Can we have a negative amount of people?
No.
No. So these questions help us figure out what the first step to do is how to adjust our graph. So we want to adjust the window settings. The minimum x value, let's see go all the way down to 0. Just sometimes a bit nicer to see that. The maximum x values go a little bit higher than what we calculated. We calculated 520, so 550. Press tab to move through. Let's start the y value at 0, and then let's have the y maximum at maybe 10 or so, like that. Why don't I see my function? Where is it? It's there. It should be 550. What did I press? Oh, I got them the wrong way around. Sorry. I got those values the wrong way around. This one should be at 10. This one should be at 550. There. Our function looks like that. So we want to know the minimum number of people who must go on the trip so that the total cost is not more than 350. So the best thing to do at this point is to graph the line y equals 350, like this, and then find the point at which those two intersect. So obviously, we want it to be somewhere in this region here. So what we do is we press Menu, Analyze Graph, Intersection, scroll across over here, click, scroll across over here, click. So if we want 350 to equal 220 over x plus 300, this implies that x is equal to, what did we get as our answer? 4.4. Obviously, we can't have 4.4 as our answer. What is our answer going to be? So the graph looks like this. Here's 4.4. Do we want to be here at 4 or here at 5? Read the question. The minimum number of people who must go so that the total cost for each person is no more than $350. So we want it to be no more than $350. We need to be in this zone. I think it should be green. We need to be here in this part of the graph. It's not acceptable to be in this part of the graph because then the cost per person is more than $350. The cost for 4 people is more. So if I just press menu, trace graph, and then type in the value 5, enter. So it's going to be $344 per person when 5 people go. So this means that x is equal to 5. So we will answer with a wordy answer when 5 people go. The cost per person is $344. Okay, homework for today is we have a section from the textbook. I didn't have to write the questions myself. I was watching. So if you go to the Google Classroom, on the classwork, you can find rational functions. There is a section from the textbook. I think you used the textbook last year. You're familiar with it from last year. It will explain a lot of the stuff that we have done here. And then at the end, you can find the practice questions. They come right at the end. So you've got the reflection questions, the modeling ones, and here on evaluating homework and practice, this is the homework questions. So do a selection of these. You don't need to do all of these. Do a selection. And you can find they provide some selected answers to this. Some selected answers. So on this function that we've drawn here, we need to sort of state what the domain is for the function. So what would be a suitable domain for this function?
X is 4.4 to also
No, it doesn't have to. The function doesn't have to answer the question. The function is the entire function. But what would be the lower bound of the domain of the function? What's the smallest number of people you can divide the cost of a car amongst?
Wow.
What's the largest amount?
Technically 8 billion, but
Okay. What's the biggest car you know of? How many seats are in it?
48.
You're going to find difficulty finding a car with more than 7 seats. It becomes a minibus at that point.
But like more people can use it.
So you can typically rent you either get a 5-seater car or a 7-seater car. It doesn't come up with many more seats than that. What else do we need to say about the function?
The Wi-Fi.
Can we have 4.4?
No. So it's hard.
It can only be an integer value. So this function can only have those 6 values. All right, finished for today?